Okay, thank you. My name is Sergio Ballesteros, data scientist at TomTom. And with my colleague Kia, we're going to tell you how we are using Databricks, Delta, and MLflow to perform geospatial analytics in a couple of use cases, and how it looks overall in the company. So first, a little bit of background about what we are working towards. So this is the vision that we have about the world. So we want a road network that is safe, that there is no congestion, zero emissions, and also that is autonomous in the far future. But in order to get there, we need to build a series of services and products. Some of them are, for example, this one, map. Then we have other connected services like traffic, live traffic information, and also other types of maps, like the maps that will be used by the cars of the future. In order to build all these, we need a very important component, which is in the end data. We use many different types of data. We use car sensor data. We have these vehicles that are going around the world and they are taking pictures of the road from these cameras that you see. And with this, we can extract information about where the lanes are located and so on. We also have community inputs. So the people who are using our apps, they can report if there is a speed camera or that a speed limit has changed, and we can update the maps in this way. We also scan with the scrappers the web, and we use natural language processing to detect if there are going to be important events that are going to block the roads, for example, marathons, and then we can update the map according to that. But the main source of data that we have is anonymous location GPS traces, latitude, longitude, and timestamps. And we have a lot of them. We have, every day we collect more than 700 million kilometers of this. And if you plot a heat map, this is what you see. I think it's beautiful. You can literally build a road network just by building a heat map. And not only that, you can also see that there are people using their smartphones on ferries, and you can start building these paths, even on planes, and you can see where people are flying from one way to the other. But how do we collect all this data? This is overall the architecture of how it looks like. We have 600 million devices that are connected to our servers. Mainly, these are smartphones, personal navigation devices, and vehicles, cars, trucks, etc. They are sending all these geo-coordinates and timestamps with some metadata to a Kafka server, or several Kafka servers that are located throughout the world, and we collect daily 80 billion data points. So that is a lot of data. We have some teams that are listening to several Kafka topics here, and they are building their maps and their live traffic services and provide this as APIs to our customers. But everything that goes through these Kafka servers ends up in one data lake or archive, what we call the float car data archive. And we keep data as long as the retention policies and the legal laws and the legal privacy laws and the contracts with our clients allow us. And in total, around 5 years of data is 150 trillion data points. So we are talking an order of magnitude of almost a petabyte. What we have seen is that in terms of analytics, many different teams throughout the company were connecting to this data lake, and they were doing all the same steps of an analytics project, which is to explore the data, pre-process it, clean it, remove outliers, etc. Model when there is something to model, and deploy when there is a model to be deployed. This was very, very inefficient because everyone was doing pretty much the same. When you have GPS data, you have to, most of the time, clean it in the same way. You want to remove the outliers because there is noise when you are driving in a city. The points are not located in the roads, but maybe they are far away because of the signal, etc. So in order to standardize this process, eventually we moved this archive into the cloud, to Azure, Blob, and we decided to take some part of this data, that the data that we are interested in, and pre-process it, removing the outliers, etc., and use Delta Lake to have some kind of version control over the data. So in this way, at the beginning we had messy GPS traces. Now we have more like clean, standardized traces, but it still is not enough. And we wanted to extract more information about the traces that everyone was doing. So we generated another database that we call root features that contain information about what is the country where the user is driving, or how long was the trip, what was the local time, things like that. And it turns out that having it in this way, we just connect to each one of these tables, and we run several use cases there, thus minimizing the time that we have to spend by pre-processing again and again the same data. And in the end, we can also plot the results of this analysis in dashboards, for example. These are the two use cases that we are going to cover today. One is called IQMaps Analytics. I will get into that later. And Kia will talk about the destination prediction use case. So, for IQMaps, what this product does is that it tries to solve this problem, which is that smartphones they work better for navigation purposes than in-dash systems. There is a reason for that. It's because usually smartphones have one type of map that we call online map. It's a sort of a streaming map. As you are navigating, you are downloading the part of map where you are located at. Usually, in-dash systems like this one, you download a big map, for example, the entire map of Europe, and you have this base map, you drive, but usually people don't update it that often. This is how one of these onboard maps look like. This is in the entire Europe, and is divided into small regions. Each one of these regions weighs about 50 megabytes. So if you combine all of them, it's about 16 gigabytes. And the standard process to update the maps have been to either take it to a car dealer, or maybe taking a micro SD, plugging into your laptop, downloading a new map, and so on. So it's quite messy. So there needs to be a solution to making those systems better than the smartphones. You might be wondering, why not just cellular map updates? Now many vehicles come already with a SIM card, and then just keep downloading the map, so have always the last version. So it turns out that these SIM cards are being paid by the OEMs. And when you multiply the megabytes that one vehicle downloads by the number of vehicles that the OEM has, these are very big numbers. So we are talking about a very high cost to just keep the entire map that the user has downloaded updated. So there needs to be a balance. There needs to be like a sort of a smart system that updates only what you want. And this is where the IQMaps product comes in. It turns out that there is this fact that 98% of the trips of a given user are within a radius of 150 kilometers from the most frequently visited points. So why not combining this fact with the previous map and download the regions that are within this certain radius? This is how it looks like, an example. You have someone that is living in blue, in the center of the blue circle of the bottom, and is commuting to work to the center of the other circle, right? And if you have this strategy about updating the map that is, of the regions of the map that is within this 150 kilometers radius, the purple regions are the ones that are being updated. So that is nice. The driver is always driving through updated regions, and if in the future, within the next month where the map is still updated, drives, for example, to the west, the user will drive still to a place where it's been updated. So that is a good user experience. However, you see that there is this region in the upper left corner that is just barely touching this blue circle, and it still is being downloaded entirely. So maybe this is a little bit of wasting data. But again, when you multiply by millions of vehicles, this is a lot of data wasted. We could say, okay, so decrease the radius and select something that is very small. Let's just say 0, just to go to the extreme. And you will have these two regions that are being downloaded. However, data usage is minimal, but user experience is going to be also bad, right? So the question that we wanted to answer, in order to get a data-driven decision on how to set this feature on this product in a way that we can prove that is sort of optimal, would be what is the most optimal radius. But how can we do this with a product that hasn't even been launched yet? Because this is still going to be launched. So the answer was to perform simulations on this with a lot of data. And for that, we thought, okay, let's do it in a laptop. Then we thought, okay, this is just simply unfeasible because there is too much data. Why not on Databricks, right? So I will walk you through a demo that I'm going to zoom in because maybe it's going to be too small. And if someone cannot read it, please let me know and I will zoom in even more. But I will walk you through the entire notebook of the simulations. It's been, I have speeded it up a little bit. But this is how it looks like. First, we load some dependencies and we define some functions. The actual code, it doesn't matter that much. But you are going to see some plots about what is going on here. So instead of using real data for our users for this demo, we are generating some fake data, but this would represent a real scenario for one single user. So if we plot it, which is done, by the way, with the volume library in Python, this is how it looks like. So this, it turns out, that is a French driver that looks like live in the center of Paris, has a few weekend or holiday trips somewhere far away, and is commuting, it looks like, to one city or village that is called Melun. Okay. So this is how it looks like when you query from the data lake of traces. That data was generated manually, but this is how it would look like in a Spark. You have this nice data frame that in one column you have the latitude, and another column you have the longitude of each one of the points that compose the trips of the user. Then you have an index, because this is there is a time dependency. You have a trip ID and a device serial. So in this case, we're only considering one single device. But if you had millions of devices, it would be just same type of rows concatenated one after the other. So now we are going to build some ground truth. We want to know which ones are the regions where the user is actually driving through. And then ideally, in the ideal world, this is what we want to keep updated all the time. So here we have in green the map regions, like you saw before in the other image, that compose France, and they are being updated on a monthly basis. Or they should be updated in a monthly basis, ideally, right? And the ones that are in gray, they are irrelevant for this specific user. Okay, so in order to simulate this update mechanism, we only keep the origins and the beginnings, the beginnings and the end points of the trip, and we are going to calculate the distances to the boundaries of the different regions. Because when we have the distances, then we can sort of compute this radius, right? We define as well an MLflow experiment with these few lines. And this has been sped up. And this is how it looks like. So there is this point that was the beginning point of one specific trip that had a distance to Albania of 1,473 kilometers, and so on for the rest of the regions and the rest of the origins and destinations. Yeah. Okay, so now that we have pre-computed all the distances, what we can do is to simulate this radius changing from 0 kilometers and increasing in a step of, for example, 5 kilometers, and see how many regions and which regions are being updated. I didn't run it until 150 kilometers because you will see that it is not necessary. And also, this is in a for loop. So for every iteration, every step of the different radiuses, we log the precision and the recall and the values of the radius. Precision and the recall can be computed because we have the ground truth that we have built. And if we go to the MLflow experiment, we can see that I have been running several experiments with different code, and also the precision and the recall is being computed for this user, and we can study the characteristics of these curves. Okay, so what we see here is that for a radius of 0 kilometers, the precision is 1, which makes sense because all the regions that are being downloaded are relevant, but the recall is not good. It's only 67%. So that is bad, and we are not retrieving everything that is relevant to this user. If we keep increasing the radius, when we reach 15 kilometers, the precision is decaying because we have downloaded something that is not relevant to the user, but still we haven't downloaded more relevant stuff for the user until we reach about 30 kilometers. And then it becomes, it looks like there is a plateau, right? If we visualize this, again in the map, for a radius of 0 kilometers, this is how it looks like. So the region where the user lives and probably works is being always updated. And it has been, at the end of the month, also updated this region in the north and this other region, and this region also in the south has been updated. But these two regions where the user was driving through were never updated with a strategy of 0 kilometers radius, right? But if we expand this radius, maybe there is a point where we are starting to download this one of these red regions. And that actually happens for the value of 30 kilometers. Yeah, and here we see something interesting, which is that this radius is just barely touching the border with this region that is relevant, but there is a trade-off. That is that we are downloading stuff that we don't need. In this case, these points correspond to the map that is representing the ocean surrounding England. And still, this region is quite far away from every single other end point or starting point. So it's going to be quite hard to download or to detect with this mechanism. For the radius of 50 kilometers, we see that there is not much improvement either. And in fact, we are starting to download other regions that are not relevant, like this one. Yeah. So more is not better in this case, right? That was an example with one single device. So the idea of the simulations is that what if we just take 500,000 trips from 10 months of data from tens of thousands of devices and compute the same thing? So it turns out that when we do that, things look a little bit better. And it turns out that for 150 kilometers radius, which is not even displayed here because it's just too far away, there is not much benefit because the data consumption would be too high. You would be downloading a lot of stuff that you don't need. The precision is very low. But instead, when we go to radius of around 10 kilometers, something like that, you have that the precision is not too bad, and the recall is it looks like it's starting to reach a plateau, right? So in the end, this was just a data-driven decision, and the insight here is that you don't need to have this very big radius. A small radius would work sort of fine, but you are going to need to have a complementary update mechanism to keep the map up to date. Because still, if we have that the recall is 98%, this might still mean thousands and thousands of users having a bad experience at some point in their trips. In order to have a more intelligent mechanism, I will hand it over to Kia, that she will present what she has been working on, destination prediction, second use case.
So, hi everyone, my name is Kia. I'm a direct colleague of Sergio, and when I first started in the team, I actually worked on a use case called destination prediction. So destination prediction is a feature that you'll find in our navigation services. And basically what it does is tries to predict where you're going. So whenever you start your navigation device, it will give you some sort of prediction. Maybe it's a Monday morning and you usually go to work. So it suggests to you, shall we navigate you through your work? And it will show you all the live traffic and the speed cameras on the way. And this we do to improve the user experience so that users can actually get going and don't have to bother typing in their address or just get going as quick as possible. So what does that look like in practice? So here we have some UX of what that looks like. So basically you get some suggestions for work or an address, and you just have to click where you want to go, and it just automatically navigates you to that point. So now that we know what destination prediction is, I can tell you that it's been a feature for already a long time, for several years. And the approach first was a rule-based solution. And this was actually causing some frustration in our users. It wasn't working as well. We weren't working with a lot of data. We didn't have a lot of data to work with. So that was the previous approach. Now, with the new Delta Lake technology, we were actually able to extract data from our floating car data archive and extract it into a Delta Lake object, and easily use this to do machine learning. So this is actually the new approach that we start using. So now we have a lot more data to work with. We can do a lot more experiments because we're using Spark, and hopefully improve our service in that way. So let me show you what the data is that we are actually working with. So a prerequisite of this data is that we need pseudo-anonymous traces, which means that there is some kind of device ID which allows us to connect one trace to the other and say that this is from the same user. So that doesn't mean that we know actually who this person is, but we know that certain traces are from the same person. And we have to use this because we have to personalize this service. So the original trace data that we use is actually 230K device serials. So this is from our speed camera app, and it actually, when you start the app, it asks you, is it okay if we collect your data in the sense that we want to improve our service? So we use this data source. And first we have to do some data prep, so a bit of a code snippet here. Some of the traces are caught during midnight, so then actually the trace is not complete, so we have to filter these out. Another filtering is that we want to eliminate all the trips that end at a speed that is more than 5 kilometers per hour, because then we do not actually know what the destination was for that trace. And some other prep steps like changing meters per second to kilometers per hour, just for ease of use. So that actually leaves us with around 140K device serials that are still left. So then we have to create a model separately for each user because each user has its own destination sets, which means in a classification problem, you'll have different labels for each user. So that means we have to create a separate model for each user. And in order to create a model, we thought, well, you need at least 50 data points to extract some kind of generalization. So that cuts it down quite a bit. We have like 3.5K device serials left. And then another trim is the device serials that were feasible for modeling, which is 2.5K, which means that these users have more than one actually favorite destination that they go to. So some users go to a lot of different places, so they don't have favorite locations. Think of taxi drivers, for example. And other users go to the same place with this app. So we can actually model, or we can model, but it doesn't really make sense, right? So the features that we have, so this is per user, is where did your trip start? What was the speed that you were going at? Is it a weekday? What kind of weekday? And then also some historical information, like where did your last trip go to? Where did you go to last Monday? And this is all to predict where are you actually going. And as Sergio said in the beginning of the talk, we have geospatial traces. So that means we have latitude, longitude, and timestamps. So how do you actually extract labels from that, right? So we don't know if this is your work address or home address. We just have the latitude and longitude stamps. So for that, we use a clustering algorithm called dbScan. And that actually clusters destinations together. So you see that this is a favorite location, for example, for a user. And then the red dot would be a noise location, what we call, which means you've only been there once. You don't go there that often. We cannot really try to predict that. So now we have our features and our labels. So what we do is we use a pandas UDF function. And some of you might already be familiar with that, but for those of you that are not, a pandas UDF function basically allows you to run this function for each user. So you give it a data frame, and it just runs, basically for each user, it runs through this code. So what this code does is it stores the user ID, it stores the data historically, it actually imports this tune model crossval function, which I'll get into later. And it outputs the best classifier that you can get for that data. And then it tests on the test set. So how well is this doing on the test set that we have? And then we store this into a data frame and we output the results. So then we have for each user ID, we have a classifier that is working best for them and also the performance measure. So how do we do this cross-validation? This was actually a bit tricky because, of course, we have some time series involved. So the historical data should be ordered. You want to train your model on the most historical data and actually test it on the most recent data. So what we do is actually, because this is also the most real life, real life way of how the model will be implemented, because it's going to be an onboard navigation model, is actually we have a classifier, let's say a random forest, with certain parameters, and we train it on trip 1 and trip 2. And then we say, okay, being fitted on these 2 data points, can you predict trip 3? And then we actually store that prediction. And we do that iteratively. So we do that also, we train it on trip 1, 2, and 3, and then try to predict on trip 4, etc. And we go over it until we are arriving at trip 10, basically. And then we have a prediction for each of the trips, and then we can actually calculate the accuracy with the ground truth that we already have. And we do this for each algorithm separately. So this is a loop. So say you want to try a random forest and also a KNN, then you would do this once for a random forest and then another time for a KNN, and then see what is which algorithm is giving you the best performance. So you can imagine that we have to do a lot of experimentation. We have to create separate models for every user, and we also want to do this iterative cross-validation approach with multiple algorithms. So yes, we have to use Spark for this. Let's see if I can show you that in a demo. So this is actually a bit different of what I explained, because for the demo, we couldn't use real data. So what I did now is I got traces, let's say for one user, and then I'm going to try to see for different algorithms which actually works best. So in the use case that we did, we actually only logged the best model per user. But now I'm going to store the results for each algorithm that we try for one single user. Okay. Yeah, so first we import libraries, and of course we initiate an MLflow project, which allows us to track the results. So we run that. So you can see that actually it's created here, the MLflow experiment, and then we load the data set. So this basically loads the data set, sorts it by value, divides it into X and Y. And actually what we want to do, I scrolled down, because this is basically the point of the whole code. So I have a lot of functions that I call, and I'll get into that later. But basically the point is we have this tune model cross-validation function, which I created. I give it an X and a Y train set, and then actually outputs for me which is the best classifier. So that makes it very easy for me. And then I give this classifier and the same data frame, but also the test set, and then output the test and accurate results. So yeah, let's look into this tune model cross-validation function. So this actually allows me to give different parameters to this function. So what you see here is that I store the parameters for the random forest, in this case, this is an example, that I want to test. So I want to use 50, I want to try 5 trees, and I want to try 50 trees. And basically, I can just keep adding to that, and I can just run the code, and it will just do all the work for me. So I make this name tuple object, which gives the name of the classifier. Also, this is random forest classifier, so this is just an sklearn model. And then the parameters that I want to test. And then I give this to this grid search function, which is shown below. Let's see. Yeah, so then I call actually the cross-validation function, which I'm going to explain next, with the parameters. So the model config is the parameters basically that I want to test. And then I give this to this cross-validation function. So if you have like a very simple way of doing cross-validation, you could also use like a grid search function from sklearn. But because I want to do this time series cross-validation, I have to create my own cross-validation function. So basically what we have here is that for each parameter, can you read this in the back, by the way? Is it? No. Let me zoom in a bit. Seems like I cannot zoom in any further. But basically for each set of parameters in this model config that I stored, I want to try to test how they work. And then I want to have this function output the best model for me. So this cross-val best model function is up here. Let's see. So it's this one. And basically it fits the model the way I want it. So the time series cross-validation method that I explained before basically runs that and then calculates the accuracy once it's done, and also the precision and recall. And then it actually compares the model that is outputted to the current best model. And that's how I iterate. So in the end, the output of this whole function will just be the best classifier with the highest precision, because I want to tune on precision. And then in this case, each of these metrics are stored in an MLflow experiment. So you can see that here. So I store the validation accuracy, validation precision, validation recall for each of these algorithms. So let's see. Yeah, so then another function that I have, so this is the last function I'll explain to you, it's just a very simple, you give it a train and a test set and it fits the model for you and a classifier and it outputs the accuracy. So this is just what I use to output the performance on my test set. So now I have all these functions. I can just basically insert all the parameters that I want to test and the algorithms that I want to test, run it, and then it will give me the best classifier for the X and the Y train set that I've given it. So yeah, if I run this, let me just skip that a bit. I think it was around here. Yeah. So now the output is like a random forest, which works the best. So all the parameters, then the performance on a validation set, the performance on a test set. So this is the classifier that I want to use. But then also I can see in the MLflow project what actually happened. So I have to zoom out a bit because I need the whole screen. But this just shows all the different experiments that I've run with all the parameters and also the metrics, and then I can actually search. So which models actually outputted precision that is more than 85 in this case. So these are 2 models, and then I can actually click on one of those and see, because sometimes you want to have the model that has the best precision or accuracy, whatever, but you also want to have a model that is training very fast, right? Sometimes you have an application where you need fast models. So you can also see how long it actually took to run this model. And then in MLflow, you have this model pickle object where you can actually download the trained model. So that makes it very easy to deploy it into a REST API, for example. So yeah, that is basically my talk, and we have 1.5 minutes left, so that's good. So yeah, thank you for listening. If you have any questions, I think it's best to just come here and take it offline, because, well, we have 1.5 minutes, but.
Yeah. First of all, let's give him a round of applause.